He wanted this week.
Mm.
But
rain soon though. Like,
yeah,
I'd be in the
that's what the group said. They were like,
I'd be in
we're not gonna really get much done with it raining.
I think we got them yesterday, which is what I thought we were doing.
Yeah.
We can't really do much until like next week when it dries up.
We went to go find his name's Tony with the shop. Yeah. We went to go look for him, but he wasn't there. So I think Dylan said he called him because we were looking for the auger because we were going to try to go do it today. But then I also told Dylan, I was like, pretty soon or 8 1 before he started digging. He's like, that's a good point. So we had to call him, and he said it's going to be at least a couple days. Hopefully the rain doesn't wash away what they mark.
I don't know. Maybe it'll waste your life there or something.
Hopefully.
Either way, we're going to have to wait a few days at least.
Mm-hmm.
Did you have anything to say about the proposal?
He had it with him because Dylan turned it in at 8 yesterday.
Yeah.
And I guess they just haven't graded. I thought he did because I was like, reason.
Yeah.
But he says he's going to grade it between after the meeting and this weekend.
Okay. The last time the draft was like in like an hour.
Mm-hmm.
It was done. So I thought he'd get done by the meeting yesterday.
Yeah, I kind of thought that too. He said we're going to meet next Wednesday. I don't remember if they told you or not.
Yeah.
So we're not. Monday we're going to do it next Wednesday, and then I think he said Wednesday after that.
We're just meeting Wednesdays.
Yeah. So far he said unless something comes up and he don't tell us otherwise.
Yeah.
But at least the next couple Wednesdays. He was pretty adamant about us trying to get something done this week. But like you said, I mean, it's supposed to rain, so they like.
What can we do this week?
Yeah.
Because I was thinking about that yesterday. Like we're supposed to get soil samples and do testing. We can't test over something we don't have. So.
I told Dylan, but we probably need to get on this like 2 weeks ago, or maybe not 2 weeks ago, like a week ago. I was like, well,
what can we do? Do we have to wait for our curbs before we can pull soil samples?
I think so, because if we go out there and start digging, and we hit like a water line or a gas line.
Well, they're supposed to be like 2 feet deep. Or is it 18
I think that auger goes like 3 or 4.
Okay, yeah.
Because I thought about that too. I was like, well, we'll figure this out and start digging.
What are they going to do?
Dylan said that a water line isn't that bad to fix, but a gas line is.
Oh, yeah. I've heard of fixing before. Gas lines are a bitch. Water lines you just kind of bend and like stop it like a water hose almost. But like, as long as you got something to clamp it closed, you can put it back together. Gas line is just go.
Yeah, that'd be kind of dangerous though. Might want that too. Go by from doing testing and stuff.
Yeah.
So he said he didn't want that with us.
So once the rain clears, we'll be fine.
Yeah.
So we can start everything then. We know what we have to do. We just have to actually get it.
He said to get like 2 buckets of sand per drill, like whatever we drill. So we get 2 buckets full.
Good morning, everyone. Today we're gonna solve more examples on using the slope deflection method in drawing the internal force diagrams, the shear force diagram, the bending moment diagrams in beams. Okay. Let's start with this example. Okay. I don't want to solve it. I want you to solve it. Okay. Just let me know what to write over here. Just go through the steps. Okay. I just want to see how you apply the steps. What are the steps for solving a beam or drawing the internal force diagrams, okay, for a beam using the slope deflection method? I'm not going to say. You have to say. One of you have to.
Bring the structure.
First step, break. Okay. So the first step here is break the structure into individual beams. How many members we're going to have here?
3.
Which is A, B, B, C, and then C, D. Okay, why, after breaking it, what would you do? What's the first step? Breaking it. Find the kinematic degrees of freedom. So you have to do this node by node, the start, the end of each of those members. So let's start with member AB. The start is point A. What are the allowed degrees of freedom at point A? How much is theta A? How much is delta A?
Both are 0.
So delta here is 0. Theta A is 0. Why?
It's fixed.
Because it's fixed. What about point B? Delta B, how much is delta B?
It's unknown. Unknown.
0. Why? Because you have a pin support that prevents the point from moving up or down. What about theta B?
Unknown.
It's an unknown. Okay, let's move to the second member. Delta B. 0. How much is theta B? The same as in member AB. Okay, let's move to the other end. Delta C is 0. Theta C. How much is theta C? Unknown. Let's move to the last member, CD. Delta C is 0. Theta C is the same value as the one in member CB. And then for point D, how much is delta D?
0.
And how much is theta D? 0. So how many kinematic degrees of freedom you have in this problem? So here you have 2, which are, what are those? Theta B and theta C. 2 unknowns. You have 2 unknowns in this problem. You won't be able to solve this problem using the slope deflection method without knowing the magnitude of theta B and theta C. Okay? That's why we started, doing this, breaking the structure and finding the kinematic degrees of freedom. Be sure you won't be able to solve this problem without knowing theta B and theta C. That's for sure. And then, what's the second step? Okay, so in the slope deflection equations, you have the term for the fixed end moments. So you need to find the fixed end moments, okay, in each side, okay? So let's start finding the fixed end moments in each side of each member. So again, here we have the 3 members, AB, BC, CD. The fixed end moments are the moments due to the loads. What loads do you have in member AB? Distributed load with an intensity of 15 kilonewtons meter, and the length is 4 meters. What about member BC? How long is the length of BC? 4, and it has a distributed load of 15 kilonewtons meter as well. Kilonewtons per meter. What about member CD? What are the loads in member CD? One concentrated load right in the middle of 30 kilonewtons. So now we want to find the fixed end moments. If you have a uniformly distributed load, how much are the fixed end moments?
WL squared over 12.
WL squared over 12. Both are equal to each other, right? So how much, and they are in this direction, okay? You can find the direction from the back of the book. So W, how much is W? 15. How much is L?
4.
So this fixed end moment is equal to 20 kilonewtons meter. And here the same magnitude, 20 kilonewtons meter. What about member BC? The same, WL squared divided by 12. W, you have the same W, you have the same length, so this is going to be 20 as well. What about CD?
PL over 8.
Okay, PL over 8. How much is P? How much is L? P is 30, L is 2 or 4? 4 divided by 8, so that's 15 kilonewtons meter. Both sides are equal, so 15 kilonewtons meter. So that's the fixed end moments. Why did I find the value of the values of the fixed end moments? You need them to write. Going to write the slope deflection equation 6 times. So you start with member AB. So the slope deflection equations you're going to write it at both ends of each member. So let's start with member AB. So what's the first end of member AB? What would you name this? MAB. For EI over L multiplied by what? Theta A. Then
plus 2EI over L
plus 2EI over L
plus theta B
minus theta B.
minus 6EI over L squared
Multiplied by what? Delta. What else?
Plus fixed end moment.
Which fixed end moment?
AB.
AB. So let's start applying this equation. How much is theta A? 0. How much is theta B? Unknown. How much is L? 4. So here we have EI divided by 2 theta B. How much is delta? 0. Both ends, there is no delta, so the total, the differential settlement between the two, or the differential deflection between the 2 points is 0. How much is the fixed end moment AB? 20. Positive or negative? Clockwise is positive.
That's
So,
negative. Yeah.
so it's negative. Okay? It's counterclockwise. Okay? So that's MAB. As you see, you cannot find MAB without knowing theta B. Okay? So let's name this equation, equation 1. let's do the same for the other end of the member. Now, what would that moment be named? The other end of the member? MBA. And that's equal to, just apply the same equation, just 4EI over L times theta B. Minus 6EI over L squared. Delta plus fixed end moment. So 4EI over L theta B. L is 4. So here we have EI theta B. Theta A is 0. Delta is 0. Fixed end moment BA. Positive 20. So that's equation 2. And then you do the same for member BC, the second member.
Since they're identical, wouldn't it be the exact same? Since they're symmetric, wouldn't it be the exact same?
Yes, but the degrees of freedom at the ends are different. Okay? The equation, there is some similarity between member AB and member BC. They have the same length, they have the same load applied on it. But the degrees of freedom here you have those are being 0. Here this is not 0. Okay? So I have to write them again. Okay? So M, what's the first end of the member? BC, MBC. What's the equation? 4EI over L times theta B.
Plus 2EI over L times theta C.
Plus fixed end moment. Which fixed end moment? BC. So how much is L? 4. How much is theta B? Unknown. So here we have EI theta B plus 2EI over L, so L is 4. How much is theta C? Unknown. So here we have EI divided by 2 theta C. How much is delta? 0, because delta B and delta C are equal to 0, so there is no differential deflection between the 2 points. How much is the fixed end moment BC? Positive or negative? Negative, because it's counterclockwise. So negative 20. So that's equation 3. And then you write the equation, slope deflection equation at the other side of the member. What would that be? What would you name that moment at the other side of the member? CB. So 4EI over L multiplied by which theta? Theta C plus 2EI over L multiplied by theta B minus 6EI over L squared multiplied by delta plus the fixed end moment CB. So theta C is unknown, so here we have EI theta C plus EI over 2 theta B, because it's unknown. Delta is 0. And the fixed end moment is positive 20. That's equation 4. And then you go ahead and apply the slope deflection equations at the third member CD. So the first end, MCD. 4EI over L multiplied by theta C plus 2EI over L multiplied by theta B minus 6EI over L squared multiplied by delta plus which fixed end moment? CD. So theta C is unknown. The length of the member is 4 meters. So EI theta C. How much is theta D? 0. How much is delta? 0. Fixed end moment CD, how much is that? Negative 15. So that's equation 5. And then the other side of the member, MDC. 4EI over L multiplied by theta D plus 2EI over L multiplied by theta C minus 6EI over L squared multiplied by delta plus fixed end moment DC. Theta D is 0. Here we have EI divided by 2. Theta C unknown. Delta is 0. How much is fixed end moment there? DC? Positive 15. And that's equation 6. So as you see, the moment at all the ends, okay, with each member, you couldn't find any of them applying the slow deflection equation because you don't know how much is theta B and how much is theta C, and all of them were function of theta B and theta C. Okay? So what's the next step? You need to find theta B and theta C. How can you do this? You need some equations of equilibrium. How many equations of equilibrium do you need here?
2.
Why 2? Because you have 2 unknowns, so you need to write 2 equations of equilibrium. You need to find 2 equations of equilibrium. So that's the third step here. Equations of equilibrium. So now, this is our structure here. We broke it into 3 parts. Here we have MAB. I'm drawing them with the notation of the slope deflection method. So positive is clockwise. So I'm drawing them all in a positive direction. MBA, MBC. This is clockwise direction. Sorry. This is clockwise, 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 clockwise. MCB, clockwise. MCD, MDC. So you need 2 equations of equilibrium. What are the 2 equations of equilibrium that you need? Someone would say, okay, going back to structure analysis 1, the equations of equilibrium is the summation of the forces in the y direction is equal to 0, the summation of the forces in the x is equal to 0, the summation of the moments about any point is equal to 0. Yes, that's correct, but those type of equations of equilibrium are they're not going to help you here. Okay? So what are the equations of equilibrium that you can write here to help you? We said there is a very nice tip, okay? Depending on the unknown, the equation of equilibrium will look so close to it. So what unknowns do you have? Theta B and theta C. Theta is a rotation, so the equation of equilibrium, it involves forces. So the force that is related to theta, rotation, is the moments. So the summation of the moments at point B has to be equal to 0. Theta C is unknown. That means that the summation of the moments at point C is equal to 0. What are the moments at point B here? MBA and MBC. The summation of those 2 moments has to be equal. That comes naturally from Newton's 3rd law, right? For every action, there is a reaction equal in magnitude and opposite in direction. Those 2 has to be equal in magnitude and opposite in direction. That means that the summation of them has to be equal to 0. Okay? So the first equation here, the summation of the moments at point B has to be equal to 0. Those are MBA plus MBC has to be equal to 0. How much is MBA? You go back to equation, what was What number did we give to the equation for MBA? Equation 2. So that was equal to EI theta B plus 20. That's MBA. What about MBC? That was in equation 3. Okay? How much was that? EI theta B plus 1/2 EI theta C minus 20. The summation of those has to be equal to 0. Okay? So adding those, this 20 is going to cancel with this 20. And then here we have 2 EI theta B plus 0.5 EI theta C equal to 0. You didn't find or you didn't reach anything here, right? Still, you have an equation in theta B and theta C. Let's name this equation 1 for R. Okay? Let's write the second equation of equilibrium. What's the second equation of equilibrium? The summation of the moments at point C is equal to 0. What are the moments at point C? Yes, MCB and MCD. Those has to be equal to 0, right? So MCB plus MCD has to be equal to 0. So how much is MCB? This was in equation 4. So this is EI theta C, okay, plus 0.5 EI theta B plus 20. What about MCD? MCD was equation 5. That was EI theta C minus 15. The summation of those has to be equal to 0. Okay? So here we have 0.5 EI theta B plus 2 EI theta C and 20 minus 15, so that's 5. Moving it to the right hand side of the equation, so that's negative 5. And that's equation 2. What would you do with those two equations? Two equations and two unknowns, theta B and theta C, you solve them using your calculator or by hand, whatever you want, okay? And find how much is theta B and theta C. If you use your calculator, you don't know how much is EI, so just neglect the EI, and then whatever the calculator is going to give you for theta B and theta C, just divide it by EI. Okay? So let's say using the calculator over here, so solving equation 1 and 2, you're going to find that theta B is equal to 2/3, and you're going to find that, you know, just divide by EI here, okay? And then theta C is going to be equal to negative 8 divided by 3 EI. Okay? So now you found how much is theta B and theta C. What would you do with those values? Substitute back into equation 1 through 6 to find the moments at the end of each member. Okay? So that's the fourth step here. Substitute those values of theta B and theta C back into equations 1 through 6. So you're going to find the magnitude of MAB. Now you know it was function of theta B. You just have the value of theta B now. This is going to be negative 19.67 kilonewtons meter. And then MBA is going to be 20.67. No, you're not going to neglect EI. As you see here, theta B is 2/3 EI. 2 divided by 3 EI. Okay? If you go back, yeah. So for example here, equation 1. So theta B is 2 divided by 3 EI, so the EI is going to cancel with the EI. Okay? And then MBC. If you substitute back, how much MBC would be? See people getting out the calculators, that's good. Okay? But, okay, if you're running out of time, you don't have to use your calculator. You know, just by looking here, you would know how much MBC would be. Yes, it has to be equal to negative 20.67 kilonewton meters. That was the equation of equilibrium that you wrote. The summation of those two moments has to be 0. This is 20.67, so this has to be negative 20.67. Okay, for equilibrium. Okay? And then MCB. How much is MCB? Substituting back, it's going to be 17.67 kilonewtons meter. And then MCD. Again, this is going to be negative 17.67 kilonewtons meter. So here, I would like you to calculate both of them, okay, and make sure that you get equal and opposite, values, so that this is a check for you. If you don't get the same magnitude with, opposite direction, then you have to go back and check, what was the wrong thing that you did, okay? Maybe you solved the equation wrong, maybe, you substitute back here wrong, your substitution here was wrong, so you have to check that, okay? And then this is MCD, and then we only have MDC left. So MDC is going to be 13.67 kilonewtons meter. So now we have those moments, so we're just going to start drawing our, free body diagrams. So draw the free body diagrams for each member we had. So we had 3 members. Member AB, it was 4 meters long. It had a uniformly distributed load of 15 kilonewtons per meter. And now, how much was MAB? How much was MAB? Negative 19.67. What does negative mean? It's counterclockwise. So the moment over here is 19.67 kilonewtons meter. How much is MBA? Positive 20.67. Positive is clockwise, so it's 20.67. Here you have a uniformly distributed load as well. It's A, B, B, C. It's 4 meters long. And here we have MBC. How much was MBC? Negative. So it's counterclockwise. 20.67. MCD was negative, so counterclockwise. 17.67. Sorry, positive 17.67, so it's clockwise. And then MCD here, it's 2 meters, and you have 30 kilonewtons right in the middle. And you have MCD, it was negative 17.67. and MDC was positive 13.67.
I think you missed a negative sign on your EMBC.
I'm not putting the signs, I'm putting the direction of the sign. Okay? Okay? Any question here? So why did I do this? To draw the bending moment diagram and the shear force diagram. So let's say here, you need to draw the bending moment diagram. Let's start with the bending moment diagram because it's actually easier here to draw the bending moment diagram. To draw the bending moment diagram for this beam, go back to structure analysis 1. How to draw the bending moment diagram for a beam? Find the moment at the key or the critical points and then plot them and then connect those points, okay, from one point to another by straight line or a curve, right? So in this beam, let's see here. This was our beam. What are the key or the critical points? To draw the bending diagram for this beam, you need to find the moment at the critical points. What are the critical points here? A, B, C, E, and D. Why E? There is a concentrated force here, okay? Why all the other points? There is a concentrated force here. There is a concentrated force here. This is the end of the member, and there is a concentrated force. This is the end of the beam, and there is a concentrated force as well. So how much is MA? How much is MB? How much is MC? How much is ME and D? How would you calculate those? You already have most of them calculated. How much is MA? Is that positive or negative? Negative. According to what sign rule? Should you use the slope deflection sign rule? No, you're done with the slope deflection now. You're using the sign rule that you used in structure analysis 1. Going downward is negative, going upward is positive. Okay? So this moment is negative. How much is MB? 20.67. Don't add them. Okay? Is it negative 20.67 or positive? No, it's negative. It's going downwards. Okay? That's a negative moment. What about MC? Negative 17.67. That's a negative moment. How much is MD? Negative 13.67. Okay? So let's draw those. Okay? So this is the beam here. So A, B, C, D. A was negative 19.67. B was negative 20.67. C is negative 17.67. D was negative 13.67. What about ME? Here. How can you find ME?
30 times.
Take the beam at point E, take the moment from the left or the right. Okay? But here, when we go do this free body diagrams, they are not complete. Why? There is a vertical force here. AY, there is a vertical force here. We're going to name it YBA. There is a vertical force here. YBC, there is a vertical force here. YCB, there is a vertical force here. YCD, there is a vertical force here, which is the reaction, dy. So, do you know any of those vertical forces? How much is AY, YBA, YBC, YCD, YCB, YCD, dy? How much are those forces? You don't know how much are they. How can you calculate them? No. Use the equations of equilibrium for each segment. Okay? So I need to use the equations of equilibrium for each and every segment here. So here, applying the equations of equilibrium, here we have those segments. So the summation of the moments about point A is equal to 0. What are the forces here? We have this uniform load. I have to find the equivalent force to it. How much is it? 15 times 4, so that's 60 kilonewtons. So taking the summation of the moments about point A, okay, I have, let's say, counterclockwise is positive, so 19.67. And then negative 20.67, and then negative 60 times 2, and positive YBA times 4 equal to 0. Right? I don't see any acceptance here. Any problem with this equation? Just stop me. Good? Everyone's good? Okay, so from here you can find YBA. So YBA is going to be equal to 30.25 kilonewtons. And then the summation of the forces in the y direction is equal to 0. So you have 60, and YBA and AY has to be equal to 0. So Y is going to be 29.75. So AY is 29.75. Okay? And then you do the same for each segment here. Okay? You take the summation of the moment at this point, okay? This moment, the moment of the concentrated force here, the moment of this force, you inflate this by 0, okay? And then you find YCB. So you're going to find YCB. So here the summation of the moments about point B is equal to 0. You're going to find that YCB is equal to 29.25. And then the summation of the forces in the y direction is equal to 0. You're going to find that YBC is 30.25. And then the same here, the summation of the moments about point C is equal to 0. You're going to find dy. So dy is going to be equal to 14 kilonewtons. And then the summation of the forces in the y direction is equal to 0. How much YCD would be? YCD, this vertical force, how much would it be? 16. 30 minus 14. So 16 kilonewtons. So now you know those values. Okay? Why did we do all of this? Simply, those forces, I'm going to need them to draw the shear force diagram. You see, I was not required to draw the shear force diagram. I didn't need to find those or those, but I needed to find one of those. Why? Find the moment at point E. So now I'm going to take the beam at point E. Here we have ME here. Once you pick the beam at point E, here you have this vertical force. It's 14 kilonewton. And here you have this moment, which is 13.67. So ME is equal to 14 times 2 minus 13.67. So ME is equal to 14.33 kilonewtons meter. So here 14.33 kilonewtons meter. Now, all I need to do is what? Connect those points either by curve, parabola, second degree parabola, or by straight lines. Point A to point B, here to here. Is it straight line or a curve? Curve, because you have a uniform load. So how to draw this curve? you connect the 2 points, and then from the middle of this dotted line, you go up. I'm just getting a third point to draw the curve with a WL squared divided by 8. So W is 15 times L is 4 squared divided by 8, so this is going to be 30 kilonewtons meter. You have a third point here, you draw your curve through the 3 points. And then point B to point C. How does the bending moment diagram look like? A curve. You connect the 2 points. You come from the midpoint of that dotted line. You go up by W, L squared, divided by 8, which is 30 again. And then you draw your curve, parabola, passing through those 3 points. And then point C to point E. Just straight line. There is no loads, so it's straight line. The moment changes linearly. And then from E to D, there's no loads, so you have to connect them. The moment changes linearly, so it's straight line. So this is how the bending moment diagram look like. You just need to do the hatching here. This is negative, and this is positive. Negative, and this part here is positive. In the bending moment diagram, again, I'm just going to remind you with what I told you in structure analysis 1. The signs is very, very important. Why? Because the way people draw this bending moment diagram is different. Only in the US that we draw it in this direction. All around the world, okay? The negative is drawn on the upper side and the negative is drawn on the lower side. So you need to put the sign to show what, way are you using, okay? And that's the bending moment diagram. Okay? So now, we just do the bending moment diagram. We need to draw the shear force diagram. How to draw the shear force diagram? A, B, C, D, and E here. How to draw the shear force diagram? Is go back to structure analysis 1. You start from the left of the beam, okay? And you go up with the forces going up, and you go down with the forces going down, right? So at what's the left of the beam? It's point A here. So you go up. You have 29.75, so you go up 29.75, okay? And then you have 60 distributed over the length of the beam, and then 30 at point B. So you're going to go up here, 29.75, and then you're going to go down by the 60. So going down 60 from 29.75, where would you be? 30.25. And then here you're going to go up by the 30.25, so you're at 0, 30.25 here. How does the shear force diagram changes from point A to point B? You have a distributed load. That means that the shear is going to change, gradually, straight line, okay? From here to here, okay? So that's the shear force in that part. Where reaction point B was split in 2 parts. Part here, I already went up this value, and then part here, going up here, okay? How much was that? YBC, which is 30.25. So I'm just going to go up 30.25, again, from the 0 here. I'm just going to go up 30.25. So 30.25 kilonewtons. And then I'm going to go down by 60. So I'm going to end up at here 29.75 and then at the end of the beam there is YCB, which is 20.75. So you go back up to 0. How does the shear change from the beginning to the end of this segment? You have a uniformly distributed load. That means that the shear is changing linearly. Okay? I guess it's going to be crossing here. Okay? So, and this one is going to be crossing here. And then, from C to E to D, from C here, at point C, you have 16. And then the shear here is constant. There is nothing to change the shear. And then it's going to change suddenly at point E. It's going to decrease by 30. And then it's going to go up by 16. So 16 up at point C. We're going to go 16. And then the shear remains constant till point E. And then at point E, it's going to go down by 30. So it's going to end up by negative 14 kilonewtons. And then it remains constant. And then at point D, there is 14 kilonewtons up. So you end up by 0. That's a check. You have to start from 0 and end at 0. So you have some positive shear here, negative, positive, negative, positive, negative. That's the shear force diagram. Any question? So here, before we go forward, okay, I just want to discuss, okay, something with you, okay, that maybe we didn't discuss earlier, but it's, I guess now it's time for it, okay? As a civil engineer, structural engineer, okay, most probably you're going to be using the software to draw this shear force diagrams and bending moment diagrams. You're not going to do it by hand, right? You have the STAT software, maybe you have a software SAT. Okay, there are many softwares that you can use to draw those diagrams, okay? But it's very, very important that you have the sense whether the bending moment and the shear force diagram that the software is giving you, is it correct or wrong, okay? So here, usually, okay, you're going to always have a bending moment, not always, usually, okay, you're going to have a bending moment diagram that looks like this, okay? When you have a load applied on a beam, this is a multi-span beam. There is many spans, right? Support here, support here, support here, support here, okay? As you see, usually, I'm not saying always, okay? The bending moment, the moment at the supports is negative, okay? The moment at the supports is negative. And then this negative moment, okay, when you have loads here, okay, those loads are gonna push or pull the bending moment up, okay? Pull it up, okay? So usually in the middle of the span, you're gonna have a positive moment. So negative moment at the supports, positive moment at the middle of the span. Is this a rule? No, it's not a rule, okay? Sometimes, for example, if the span here is a small span, yes, the load, the gravity loads, is going to pull this up, but it's a small span, so it's just going to go up here, but it's going to remain negative. It's not going to turn to be positive if the span is small, okay? If the loads, let's say the loads that you have here, a uniform load here, were so large compared to the load that was here, again, it will pull it up, but it's not going to be, you know, big enough to change it to negative, from negative to positive, okay? But usually if the loads, if those three spans are relatively equal in load or so close to each other, the loads that are on all three spans are, you know, close to each other, okay? You're gonna have negative at the supports and positive in the middle of the span, okay? If the software gives you something different, then you have to question it, okay? Let's say You remember instruction analysis 1, you had many cases of loading, right? So let's say one of the cases of loading, you just had loads here. There is no load here. How do you expect the bending moment diagram to look like? If you just have loads here, and no load here. So it's going to be negative, 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 because you have some loads here. And then there is no load here. Actually, this one is going to be positive. Okay? Why is that? We're going to see this maybe in a, in some other example. I don't. Okay. Let me tell you why that would be. Just a quick note on why would that be. Okay, I'm just gonna erase it. So if you want to take note of it, it's not gonna. I'm not gonna leave it there. Okay. Let's say you have this beam like this. Okay. You have loads here, and there is no load on the last span here. A, B, C, D. Okay. I was telling you here, the bending moment diagram, I would expect it to be like this. Negative, 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 and then it's going to be like this, and then here's going to go like this. Why is that? If someone would give me an explanation, a valid explanation, why did I say that this one is going to be positive? This one is negative here, but this one is going to be positive. Can someone give me, if someone says so, I'll give him an extra 5 points.
Because the moment's equal to the shear.
No, I need a very clear explanation of what you're saying.
What was the question again?
We said the bending moment diagram, you're going to have negative moment at the supports, okay? And then it's going to turn positive. On this span, there was no load here, okay? So the moment here is not going to be negative. Actually, it's going to be positive.
Because
it's
fixed.
fixed.
Going to be on the unit.
Okay, this is correct. This is a sense of why it would be. But no, I need a mathematical explanation. Not just, because the deflect, yeah, you're correct. The way the beam is going to deflect, the curvature of the beam is going to be here, different. Like, it's going to be like this. Sorry. Oops. Undo. How to undo. So it's going to go like this. So the curvature of the beam here is opposite. As you see here, the curvature is like this. This one, the curvature is opposite. So, yes, but this is not this is, how you visualize the deflection, okay, the curvature of the beam. I need a mathematical explanation. By numbers, okay, by equations.
Does something to do with the fixed end moment at C?
Something to do with the fixed end moments at C? No.
Haven't encountered
But you're
that.
getting close. Huh?
Or because
The slope of the moment is the value of the shear, so there are no loads there.
Negative shear.
No. So the point here, okay? Let's see here. It all comes down to writing the slope deflection equations for member CD. Okay? So if you write the slope deflection equation for member CD, you have MCD and MDC. How would you write those? MCD. How would you write it? 4EI divided by L multiplied by theta C plus 2EI divided by L multiplied by theta D, which is 0. And then the delta, right? 0. And then fixed end moment. 0. Why 0? There's no loads, right? So here you're just going to have 4EI divided by L theta C, right? And then apply the slope deflection equation to find MDC. How would you do this? 4EI divided by L theta E, which is 0. And then 2EI divided by L theta C. And then delta. 6EI divided by L squared divided by delta. Multiply by delta. 0. Fix them moment. 0. So as you see here, MCD and MDC, okay? MDC is the same direction as MCD, but it's half its value, right? So here, this is member CD. MCD, we said it's negative, right? So it's like this, right? According to the slope deflection sign, they have the both. They have the same direction, right? Both are just this magnitude multiplied by theta c, so it has to be in this direction, right? That's what you have from the sign here. They have to have the same direction. So if this is a negative moment, this is going to be a positive moment, according to the rules or the signs of, the slope deflection, right? So whatever moment you're going to have here, how much would that moment be? 1/2 MCD. And they're going to be opposite in direction because there are no loads here. And this is fixed. Okay? Any question? So that's a sense of what you can have, okay? What you expect for your bending moment diagram, okay? As I tell you, most probably you're not going to draw those bending moment diagrams by hand, okay? You're going to use some software, maybe there are some approximate ways of analysis, okay? But at the end, you have to have the sense, okay? Is that bending moment diagram reasonable or no? It seems there is something wrong, okay? You need to have this sense, okay? Any question here? Okay, let me just leave this for you, okay? So now let's go ahead and solve more examples here. One more example here. So the example that we're going to solve now, we're actually going to solve it twice. Most probably today we won't have time to solve it twice, okay? So we're going to solve it one time today, and then we're going to solve it again next time, okay? But we're going to try to make it easier next time, the way that we're going to solve it. So 6 meters here, 1 meter and 1 meter. This is point A, B, C. So first, okay, so the problem statement here, we need to calculate theta B and theta C, okay? I'm not asking you to draw the bending moment diagram or the shear force diagram, okay? But definitely once you find theta B and theta C, you can go ahead and substitute in the slope deflection equations and find the moments and draw the bending moment diagram, okay? So I'm just, not solving the entire problem here. But since we're talking about the sense of how the bending moment diagram would look like, how would you think the bending moment diagram would look like? Negative here, okay? What about point C? Negative?
Straight line.
No, the moment at point C is 0. Why? It's a support, yes, but it's a pin support at the end of the beam. The moment is 0, okay? It's only negative if it was a fixed support, okay? And then here you have a uniform load, so you expect the bending moment to be like this, okay? And then here you have this load, it's going to pull this up, but as you see, this is 6, this is 2, okay? So it might go like this, or it might just turn out to be like this, okay? Because it's a small span. So if it happens to be all negative here, that's something that you can understand because this span is so small compared to this one. It's just 1/3 of it, okay? So you won't know before solving. But if you just, you're using the software and it happens to be like this, okay, that's fine, okay? You would expect something like this to happen, okay? So now, I would like to solve this problem. How would I do this?
Kinematic.
Break the beam into individual members. How many members here? Two. A, B, B, C. How much is delta A? How much is theta A? How much is delta B? How much is theta B?
Delta B, sorry. Zero. That one's
Unknown. How much is delta B here? 0. How much is theta B? The same unknown, okay? Same theta B in member BA. What about delta C? What about theta C?
Unknown. Unknown.
Unknown. Why not 0?
Because it's
Not fixed, it's pinned. So pin support doesn't prevent the point from rotating, okay? So what are the kinematic degrees of freedom? 2. Those are theta B and theta C, okay? And then we're going to go to the second step. We want to derive the slope deflection equation, so we're going to start finding the fixed end moments first, okay? This is member AB, and then member BC. Member AB is 6 meters long. It has a uniform load of 40 kilonewtons meter. 40 kilonewtons per meter. So how much are the fixed end moments? Those are the directions. Okay, you have to either memorize it or just, see them at the table at the back of the book. How much are the magnitude? WL squared divided by 12. W is 40. L is 6 squared divided by 12. So this is equal to 120 kilonewtons meter. And this one is equal to it. What about member BC? It's 2 meters long. It has one concentrated force right in the middle. The magnitude of this force is 60 kilonewtons. So how much are the fixed end moments? PL divided by 8. P is 60, L is 2 divided by 8, so that's 15 kilonewtons meter. And the same here, 15 kilonewtons meter. Symmetric, so they have the same value. Okay? And now you write the slope deflection equations. How many times? I'm going to write the slope deflection equation. 4 times at both ends of each member. So I'm going to start with member A, B. Okay? So MAB, it's 4 EI divided by L, theta A, plus 2 EI divided by L, theta B, minus 6 EI divided by L squared, delta, plus the fixed end moment AB. How much is theta A? 0. How much is L? So this becomes EI divided by 3 theta C. How much is delta? How much is the fixed end moment AB? Positive or negative? Negative. Theta B. And that's equation 1. Then the other end of the member, MBA. 4EI divided by L, theta B, plus 2EI divided by L, theta A, minus 6EI divided by L squared, delta, plus the fixed end moment, BA. Theta B is unknown, so here we have 4 divided by 6, so this is 2/3 EI, theta B. How much is theta A? How much is delta? How much is the fixed end moment BA? Positive 120. And then you apply the equations again. Remember on member BC. So you're going to have MBC 4EI divided by L, theta B, plus 2EI divided by L, theta C, minus 6EI divided by L squared, delta, plus fixed end moment, BC. So, how much is the length?
It's
2. The length of member BC is 2. So here we have 2EI theta B. It's unknown, right? 2 divided by 2, so EI divided by theta C. Theta C is unknown, right? And then delta is 0. How much is the fixed end moment of BC? Negative 15. So that's equation 3. And then you write the equation, apply the slope deflection equation at the other end of the member, MCD. So here we have 4 EI divided by L theta C plus 2 EI divided by L theta B minus 6 EI divided by L squared delta plus the fixed end moment CB. So 4 divided by 2, so 2 EI theta C, 2 divided by 2, so we have EI theta B, delta is 0, fixed end moment is positive 15 kilonewtons meter. That's equation 4. Okay? What's next? Equations of equilibrium. How many equations of equilibrium? Why 2? Because you have 2 unknowns, so definitely you need 2 equations of equilibrium. What were your unknown? Theta B and theta C. That gives you a hint what equation of equilibrium you need. If theta B is unknown, what equation of equilibrium you need? The summation of the moments at point B has to be equal to 0. If theta C is unknown, what type of equation of equilibrium you're going to need? The summation of the moments at point C is equal to 0. So let's draw the beam here. You have just those 2 members. You have point A, B, B, C. Let's draw the moments in a positive direction. MAB, MBA, MBC, MCB. The first equation says that the summation of the moments at point B is equal to 0. What are the moments at point B here? MBA plus MBC has to be equal to 0. Those 2 moments has to be equal in magnitude and opposite in direction. That means that the summation has to be equal to 0, right? So let's find the values here from equation 2 and equation 3. So we have 2/3 EI theta B plus 120, that's MBA, plus MBC, which is 2 EI multiplied by theta B plus EI theta C minus 15, that has to be equal to 0. So adding those up, here we're going to have 1/3 EI theta B plus EI theta C equal to negative 105. That's equation 1. Okay? What's the second equation? The summation of the moments at point C equal to 0. What moments do you have at point C? MCB. So what does this equation tell you? That MCB has to be equal to 0. Does this make sense? Yes, the moment at this point has to be equal to 0. It's a pin support at the end of the beam. The moment MCB has to be equal to 0. Okay? So that's what we have here. MCB has to be equal to 0. MCB was equal to 2EI divided by, 2EI theta C plus EI theta B plus 15 equal to 0. That's equation 2. So now you have two equations in theta C and theta B. You solve them together. Find the magnitude of theta B and theta C. Okay? So solving equations 1 and 2, we're going to find the magnitude of theta B, negative 45 divided by EI, and theta C is going to be 15 divided by EI. That is the answer that you were looking for. If I ask you to draw the shear force diagram, the bending moment diagram, you just need to continue solving the problem, okay? Draw the free body diagram of each member, okay? Find the vertical forces to draw the shear force diagram, and draw the shear force diagram and the bending moment diagram as we did in the previous problem. Any question? Okay, so as you saw here, okay? The moment at point C is equal to 0, right? We just made use of this at the very end point, okay? We didn't use it anywhere in the problem, only when we wrote the equations of the cube we did use it, right? So what we're going to do next time is we're going to try to modify our slope deflection equations, okay? If we know that the moment here is equal to 0, we're going to modify our slope deflection equations to use this knowledge, okay, from the beginning of the problem, okay, to make it easier. We're going to see how easy it's going to be, okay? If we modify our slope deflection equation to make use of this knowledge or this information that the moment here is equal to 0. Okay? Any question? Okay, so see you next time. How's the project, the seepage going? Everyone stopped reading. You should have read the rules now. Seems no one has done so. Okay.
There you go. Try Huh? I know. I read it. I was like, huh. Yeah. They're all exactly the same.